Hello. Hopefully you can hear me, and you can hopefully also see the image at the moment of the June 2014 P4P5P6 paper. It's the higher tier that I'm going to go through. If you can leave questions in the comments box as you go through. Leave questions in the comments box as we're going along. And sorry, just one moment. Just get this set up. You leave comments and questions in the comments box. I'll try to respond to a few of them as I'm going through, though I probably won't have time. But I will also allow some time at the end of the broadcast for just general questions and answers. So let's get started with looking through the paper. So the first thing you'll come to when you open the exam paper on Friday will be the useful relationships, the formula sheet. You don't need the first two here. They are for your 1, 2, 3 exam, which you've already done. So the relevant ones are in the second half of the page. We have explaining motion, which is P4. You have electric circuits, which is P5. And you have radioactive materials, which is P6. So all three of those sections are relevant to your exam. Question number 1. In 2008, Usain Bolt set a new world record for the 100-meter race. This is a velocity time graph for the race from start to finish. Part A says, what was the world record time set by Usain Bolt in 2008? Well, if we have a look at the graph here, this is a velocity time graph. It doesn't directly tell us the time here. What we have to do is you have to look to see where the graph stops. And obviously the graph will stop when Usain Bolt crosses the finish line. So looking along the axis here, we can draw a line from the end of the graph here down to the x-axis, and you'll see that comes at around about 9.7 seconds. Data can be used to show that the race was 100 meters long. Complete the equation below. Choose a word from the list: average, final, initial, instantaneous, or maximum. So the distance of the race equals the time taken multiplied by the something velocity. Well, in order to work out the distance of the race, you can use the equation, which I'm not sure if this one's on the formula sheet actually. No, speed, distance, time isn't on the formula sheet, but it's an equation that you should have known since year 7. And this is the rearranged version of it. The distance equals time multiplied by velocity, and it's the average velocity that is relevant here. Some commentators said that Usain Bolt could have got a faster time. What evidence from the graph supports this? So again, looking back at the graph, what can we see that would support that? Well, the velocity, the higher the line is on the y-axis, the faster he was running it at any given point. You can see here he's getting faster and faster and faster and faster still increasing in speed, Around about 6 to 8 seconds here, he's flattened off, he's traveling at a constant speed. And then you'll see just a little bit beyond 8 seconds, this last second of the race, Usain Bolt actually slows down. So that suggests that had he managed to maintain that constant speed all the way to the end, he could have actually achieved a faster time. So we should say something along the lines here of his velocity is slower at the end of the race. Part D, at what time during the race was Usain Bolt accelerating the fastest? Now, when we're looking at a velocity time graph, acceleration is the gradient of the graph. We are interested in the part of the graph that has the steepest gradient, because that would correspond to the fastest acceleration. or the highest level of acceleration. If we look, we've got to look quite carefully here. You see it's increasing fairly sharply in the first couple of seconds, but then the line takes a sharper turn in this region here. So we need to give a number somewhere between 2 and about 2.8. So let's say 2.5 seconds, because that would be enough to get the mark. OCR allowed anything between 2 and 2.8. And the final part of the question, all the velocities on the graph are positive. What does this mean? Well, velocity is speed in a given direction. So if you have a negative velocity, it means that the object is traveling in the opposite direction. So a positive velocity means that throughout the whole race, Usain Bolt was running in just one direction. Question number 2. Tamsin hits 2 balls with a bat. The hard ball has a mass of 0.3 kilograms. The soft ball has a mass of 0.2 kilograms. Each ball gains the same momentum. That's a very important point. The hard ball will have the smaller velocity. Explain why. Well, if both balls have gained the same momentum, then we need to use the equation for momentum, which if we go back to the P4 equation sheet here, we'll see momentum equals mass times velocity. So if momentum equals mass times velocity, that would suggest that a greater mass means a lower velocity. In order to keep the momentum constant here, you'd have to have a lower velocity if you have a higher mass. Part 2, the soft ball changes shape when hit so that it is in contact with the bat for longer. What effect will this have on the force acting on the soft ball? Again, we're going to need to take a look back at our formula sheet here. And we'll see that the second momentum equation is that change of momentum equals resultant force multiplied by the time for which that force acts. So that equation can be rearranged to get force equals change in momentum divided by the time that force is acting for. So if the if the time increases, and that's what's happening here, the ball is in contact with the bat for longer, so the time during which that momentum change is happening is getting bigger. So if the time increases, the force must decrease because they are inversely proportional. This is that kind of question, by the way, you're likely to get in the context of car safety. So airbags, seatbelts, crumple zones, crash helmets, all of those work through on the principle of increasing the length of time that a collision acts for in order to reduce the force that is experienced by the human body as a result of the crash. Because you can't do anything about the change of momentum. In a crash, the car will always change its momentum from whatever momentum it has before the crash down to 0. So you can't do anything about the change of momentum, but you can increase the time that change takes. And by doing that, you can reduce the force. So it's a similar physics there. The 0.3 kilogram ball hits a glass window with a speed of 4 meters per second. The glass will not break if the ball has a kinetic energy of less than 10 joules. Will the glass window break? Use a calculation to help justify your answer. Again, it's worth looking back at the formula sheet here for P4 and finding something that's going to be relevant to kinetic energy. And here we have kinetic energy equals half multiplied by mass multiplied by velocity squared. So let's make a note of the formula here. So kinetic energy equals half multiplied by mass multiplied by velocity squared. And we can plug some numbers into this now. So half multiplied by the mass of the ball, it's the 0.3 kilogram ball, so half multiplied by 0.3, multiplied by the velocity of the ball, which is 4 meters per second, squared. And that equals 2.4 joules, which is the unit. Excuse me. Equals 2.4 joules. By the way, in an exam, if you see a space like this without lines on, that is usually a clue that you should be doing a calculation in that space, or perhaps a diagram. If it's a diagram, they'd usually be quite explicit about it being a diagram. Certainly in any questions like this, that's the space that I expect you to show your working for the calculation. This wouldn't be enough to get all the marks so far, because you haven't actually answered whether or not the glass window will break. So to do that, we need to write a few words. We need to say that the window doesn't break because 2.4 joules is less than 10 joules. So the 2.4 joules of energy that our ball has as it hits the window is less than the 10 joules that the window needs to break. So no problem there. The window won't break. And the final part of question 2, the 0.2 kilogram soft ball hits the window at a speed of 6 meters per second, and it bounces back from the window at a speed of 4 meters per second. What is the change in momentum of the soft ball? Now, when students did this as part of their mock exam, this was a question that a large majority of students got wrong. And usually the same mistake. It's usually worth in a momentum question like this. So I've drawn a couple of diagrams. So we know that before we have the ball heading towards the window at 6 meters per second, and we know that after we have the ball moving away from the window at 4 meters per second. Now, the most common mistake that students would make here is to say that, well, 6 take away 4, that's a change in speed of 2 meters per second. It is a change in speed of 2 meters per second, but momentum is not about speed, it is about velocity. So if it's traveling at 6 meters per second and that's positive to the right, if it's traveling to the left, that's traveling in the opposite direction, we have to give that a minus sign. So the velocity as it leaves the window is minus 4 meters per second. So if we work out our momentum before, remember momentum equals mass times velocity. We can use the symbol P for momentum. That's an AS level thing. I'm just going to use it here to shorten proceedings. You don't have to use P. You can just use the word momentum. P equals mass, which is 0.2, multiplied by velocity, which is 6. So before the collision, the momentum is 1.2, and the unit kilograms meters per second. Now that's not our answer, that's just the momentum we had before. Let's call that P1, and P2 to work out our momentum after. The mass of the ball is still 0.2 kilograms, but the velocity now is minus 4 because it is traveling in the opposite direction. It is a minus velocity, so minus 4 meters per second. and that will give us a momentum of minus 0.8 kilogram meters per second. So our change in momentum is going to be the difference between these two values. So we're going to take our after, which is minus 0.8, and subtract our before from that, and that will give us an answer of minus 2. So what this is saying is that our momentum is decreasing by minus 2.0 kilogram meters per second. That is our change in momentum. We don't need the minus sign here necessarily. We're just saying that the momentum is changing by 2 kilogram meters per second. A really hard question, that question thrown in to very much identify the strongest students in this exam paper. Question 3 is the first 6-mark question in this exam paper. This was a question that was aimed at students looking for up to an A star grade. It was a relatively difficult question. We have Amir here. Amir is a long jumper. He runs as fast as he can before he jumps, and that lets him jump much further than if he'd jumped without running. So use ideas about forces and motion to explain how running helps Amir to jump further. So as with any 6-mark question, the first thing we need to do is identify our command words. So we need to be using ideas about forces and motion to explain how the running helps Amir to jump further. Just responding to a couple of questions that have popped up in the comments from the previous answer before I do this. The reason I missed the minus sign off there, it doesn't matter. You'd get the mark if you left the minus sign in, but it's a change in momentum. It doesn't matter whether the momentum's increased or decreased. It's just a difference between two values, and that's 2. And it's also possible to that you could have done 1.2 take away minus 0.8, and that would give you a positive value for 2. Both are correct. And to respond to another question quickly, yes, this will be uploaded afterwards, automatically straight after the video's finished. This will go on YouTube. Okay, back to Amir and his long jumping. So we need to use ideas about forces and motion to explain how the running helps Amir to jump further. Well, the first thing we need to say is that running increases Amir's velocity and also kinetic energy and momentum. I don't need to necessarily say all 3 of those things, but they would all get the mark in this case. So when he jumps, he travels further. We'll explain that below in a moment. It's worth here, we've talked about motion there, we haven't talked about forces. It does say to talk about forces, so it may well be worth us quickly explaining how forces allow Amir to run. So friction between Amir's shoes and the running track allow Amir to push forwards. Well, the friction allows Amir to push backwards on the running track, which creates an equal and opposite force, an interaction partner force, to push him forwards. I'm going to go into a lot of detail in this question, and you wouldn't necessarily need all of this detail in your answer to have got 6 marks, although I would say most of it you would. Now, that's dealt with the running side of it. We haven't addressed why it is that just simply being faster when you hit the takeoff board allows Amir to travel further. So for that, we need to consider the jumping side of what he's doing. So when he gets to the board, he pushes off with his feet, he pushes off the ground. Jump and gains an upward velocity. So he was running forwards, which gave him sort of a horizontal velocity forwards along the track, but by pushing his feet off the ground, now he gains an upward velocity. He's flying into the air. His weight, which at GCSE we can call gravity, pulls him back to the earth. And it doesn't matter. The only thing that's going to affect how long that takes to happen is how hard he pushed off the ground. It doesn't matter how fast he was running previously. It will pull him back to the earth in a certain time. Therefore, the faster he's running, further Amir will travel forwards in the time he's off the ground. To understand this better, imagine the extreme cases. So imagine he doesn't run at all. So he runs and he just jumps. Well, if he's not even pushing forwards at all, then he would just jump straight up in the air and land straight back where he started, and he wouldn't get any distance at all. That's the extreme. That's one extreme. The other extreme is he runs incredibly fast down the runway. He jumps up, and that allows him to travel a huge distance sideways. But in each case, the time he's off the ground is the same. It's just he makes better use of that time through giving himself that horizontal velocity. The answer I've put there would get you 6 marks. As always, when you're approaching 6-mark questions, identify the command words, really pay attention to what the question's looking for, and then what I didn't do here, and perhaps I will do for one of the later questions, but jot down some notes as you're approaching the answer. Identify the information that you know that is, well, identify information that you know that is related to the question, and then go through that information and cross out anything that isn't relevant to answering the question, because it's really important then that when you write your answer, you only include relevant information, or rather that you don't ruin your answer by talking for ages about something that isn't relevant at the expense of leaving out something that is relevant. It's really important that you are clear what the question is before you attempt to answer it. Sounds like a stupid thing to say, but it is important. Okay, question 4 takes us from P4 into P5 and gives us a data table. And the data table is for an investigation showing the relationship between the current in the wire and the power lost by the wire. It says, sketch a graph of these results on the axis below. You do not need to plot any points. First thing to do here is that the first column in a table will always be the independent variable, the thing we're changing, which in this case is the current, and that will always be on the x-axis. And therefore the dependent variable, the thing that we are measuring, will go on the y-axis. So we put power on the y-axis. Now let's have a look at these numbers. It says you do not need to plot any points. It's not asking for a really accurate graph, but we do need to have a look at the shape of this. We can see when it's 0.5, the power is 1. So when the current doubles to 1, the power has gone up 4 times. When the current doubles again from 1 to 2, the power goes up by 4 times to 16. So there's a relationship here which is not linear. It's not going up in equal steps. When the current doubles, the power quadruples. So a straight line wouldn't be correct here. What we need is a line that curves like this, showing that the power is increasing faster than the current, which you can see from the table. So Edward looks at the data and draws some conclusions. He says there is a correlation between the current and the power lost, and he says the current is directly proportional to the power lost. So the first thing to say is, yes, there is a correlation. Remember, a correlation is that as one thing increases, another thing increases. We can see here the current increases does cause the power to increase. So yes, there is a correlation. As the current increases, the power increases. That's not all that Edward said. He also said the current is directly proportional to the power lost. That isn't true. If we look, if it was directly proportional, we'd expect doubling the current to mean you were doubling the power. We'd expect to see a straight line graph. Think back to the investigations you've done. The doubling of one thing leading to a doubling of the other is directly proportional. This graph doesn't show that. It's not a straight line graph. So the current is not directly proportional to the power because it is not a straight line graph. Question number 5. Tim does an experiment using a circuit with 3 resistors in series. You can see one resistor there with a resistance of 1 kilo ohm, the second resistor with a resistance of 2 kilo ohms, and the third with one of 3 kilo ohms. Which resistor will have the largest potential difference across it? Potential difference is the energy lost by each of the charges as it goes through a component. So each charge will have to give up more energy to get through a 1 kilo ohm component than it will to get through a 2 kilo ohm component, and that will have even more energy to get through a 3 kilo ohm component. Because remember, resistance is when the electrons are colliding with the lattice of ions, the charged atoms in the metal. So if you have a higher resistance, you're going to get more collisions, and the electrons are going to give up more of their energy. So here, it's absolutely the case that the 3 kilo ohm resistor will have the largest potential difference across it because it will use more energy. The charges will lose more energy as they pass through it. Part 2 asks us to explain this, as I just said. So let's go through these. The same battery voltage causes a larger current to flow through a smaller resistance than through a bigger one. Well, this one is not true. In a series circuit such as the one we've got up here, the current will be the same all the way around the loop. That is always the case in a series circuit. The current is the same all the way around the loop. So it's nothing to do with a larger current. The second one, more work is done by the charge moving through a large resistance than through a small one. Well, that sounds very similar to what I've just said about work and energy. Work, remember, is energy. So the charge is doing more work to get through a large resistance than through a small one. That sounds correct. We'll tick that one, but let's just check the other two. Let's rule those ones out. A change in the resistance of one component will result in a change in the potential difference across all the components. Well, that is true. If I were to increase the resistance of this one to, let's say, 300 kilo ohms, then far more potential difference would be across that one than across the other one. So that one is true, but it's not an explanation for why the 3 kilo ohm resistor has the larger potential difference. And the fourth one here, the current through each component is the same as if it were the only component present, and that's not true here either. The current is the same all the way around the loop, and actually the current here is dictated by the sum of the currents, by adding our 3 currents together. So our correct answer here is the second one that we ticked. The total potential difference across the 3 resistors is equal to the potential difference across the battery. Explain that statement using the idea of work done. So remember, work done is energy. It's the same in P4 when you lift something off the floor, you're doing work on it. The battery is doing work on the charges. It is giving energy to the charges. And then those charges, as they flow around the circuit, when they pass through resistors, they are doing work on the resistors. So if you think about it, the battery is taking chemical energy and doing work on the charges to give them electrical energy. When the charges reach the resistors, they are doing work on the resistors to produce heat energy. The resistors heat up. That's what happens when current passes through them. So it follows that we can't create or destroy energy. Whatever energy the battery puts in and gives to the charges has to be equal to the energy that the charges then give out as they pass through the resistors. So let's phrase this properly. The work done per charge from battery is equal to the work done by each charge on the components. There's a video on my YouTube channel which anybody struggling with electricity might want to watch. It's about electrical circuits. It'll be in the P5 playlist, I think. What's important, it uses an analogy about students walking to school and the students being the charges, the flow of students being the current, and the lunch boxes that the students are carrying representing the energy that charges have, which is what we call voltage. If you're struggling with any of these concepts, I suggest you have a look at that video and check out other videos I'm sure are available that might be helpful. What we're saying here is that the charges always leave the battery, set off from the battery with a maximum amount of energy, and they always get back to the battery with no energy left. So the energy that each charge gains at the battery must be used up by the 3 components that the charges pass through. And finally actually it's not the final part of question 5, it goes on to the next page, but part B of question 5. In another experiment, Tim is using 100 kilo ohm resistors and 200 kilo ohm resistors. Which arrangement of resistors will have the smallest total resistance? We need to put a tick next to the correct answer. By the way, as it's always worth highlighting at this point, tick box questions, or those questions where you have to draw lines between different boxes, read the question. Pay attention to how many lines or how many ticks you're expected to place, because it's such an easy way to throw away marks if you don't. if you aren't clear on that. Here it says put a tick. There's one mark available. It says put a tick, so put 1 tick. Okay, so the resistance of a 100 kilo ohm resistor on its own, that's obviously going to be 100 kilo ohms. A 100 kilo ohm and 200 kilo ohm resistor in series. Let me just check the formula sheet. I'm not certain that they provide. Formula for this one. No, they don't. So you need to learn the equations for resistors in series and resistors in parallel. When you have at GCSE level, any resistors that are combined in parallel, they'll always be the same value of resistors. You won't have to do anything more complicated than that. So when they're in series, it's simple. You just add them up. So 100 kilo ohms plus 200 kilo ohms, that would give 300. So it's certainly not this one, because this one is higher than the first one. The next one, 100 kilo ohms and 100 kilo ohms in parallel. Well, when resistors are in parallel, and when you have two resistors the same in parallel, you divide them by 2. If you have 3 resistors the same in parallel, you divide it by 3, 4 by 4, and so on. So here we have 2 100 kilo ohm resistors in parallel. We need to divide that by 2. The resistance is only 50. This seems counterintuitive, perhaps, that you can actually get a smaller resistance than any of the resistors that go into it. But think of it in a parallel circuit. By providing a second resistor, you're actually giving the current more options, more directions it can travel in. It's effectively like giving it a wider wire, which would reduce the resistance. So that's why the resistance goes down when we have them in parallel. And 100 kilo ohm and 100 kilo ohm series, we just add these together in series, so that's going to be 200. Our correct answer then is the third one down here, which is 50. And moving on to the final part of question 5, Tim builds a circuit to test a motor. He decides to increase the voltage. He tries adding an identical battery in parallel with the first battery in parallel. What will happen to the voltage and the current in this circuit? Put a tick in the box next to the correct answer. So this is equivalent to him putting another battery up here in parallel. And the first thing to remember is that in a parallel circuit, the voltage is the same in each branch. So in this case, the whatever voltage he's got here on this battery, they're the same type of battery as well anyway, he's not going to increase the voltage by doing this. The voltage will stay the same. So straight away, we can rule out this one because it says that voltage increases, and this one because it says that the voltage increases, and this one because it says that voltage decreases. So it must be the last one, that voltage stays the same, because in any parallel circuit, the voltage is the same in each branch. And part 2, Tim tries using a transformer to change the voltage. The transformer does not work in this circuit. Explain why. Well, we have 2 types of electricity you should be aware of in outline. One is direct current and the other one is alternating current. Direct current is the one you've almost always come across in your school career. It's what batteries produce. It's when the charges, the electrons, flow continuously in a loop from one end of the battery through the circuit and back to the battery. It's a very simple way of understanding electricity. Alternating current is when, instead of flowing continuously around the loop, the charges, the electrons actually shuffle backwards and forwards, changing direction in the wire 50 times every second. It still transfers the energy, but the electrons themselves aren't flowing in a loop. They're just vibrating backwards and forwards 50 times every second. The electricity that you get from the main supply is alternating current. If you plug into a socket, that is alternating current. Now, transformers only work using alternating current. If you want to understand how transformers work, I have made a video explaining how transformers work, so it's worth checking that out. And I explain in that video why it is that it has to be alternating current. What we need to say here is that this is a circuit with a battery in it, and batteries use direct current, DC. Transformers only work with alternating current, AC. And that's 2 marks. And on to the 6-mark question for P5. Just having a look at some of the questions that have come through on the comments. Why does voltage stay the same in a parallel circuit, says Pyle. I would suggest you watch the video, as Akshat said, I suggest you watch the video that's on my YouTube channel, in which I have the analogy with the schools and the students walking to and from school. I think it's probably the best analogy for thinking of. And it is quite long, but it's 10 minutes. You'll have a much better insight, I hope, into parallel series circuits, current and voltage. Everything should make a little bit more sense, I hope, if you watch that. And also, Robert, yeah, I'm only going to go through this paper in this video. However, I will do maybe half an hour afterwards of just general questions and answers. So question number 6, here we have a filament lamp emits light when a current is passed through it. This is a hard 6-mark question, and from what I remember of marking your PPEs in January, in February, it wasn't successfully done by many students. So let's spend a few minutes on this. It says the filament wires in the lamp are much thinner than the connecting wires. When the lamp is turned on, the filament emits visible light, but the connecting wires do not. Explain why this happens. So we can see the electricity comes into the light bulb along these connecting wires, then it passes through the filament and back out. So it's passing through both the connecting wires and the filament. But the question is saying the filament glows, but the connecting wires don't. They've got the same current flowing through them because they're in series. So why is that? Well, the first thing we need to think about here is resistance. And one of the problems I think I came across when I read many of the answers to this question in February was students being confused between the word resistor and resistance. Resistance is a property that everything has. You have resistance. Your body has resistance. It is simply the property of any material that opposes electrical flow. So if something has a higher resistance, it will be more difficult for current to pass through it. A resistor is a component, just as Tim was using up here, he was using resistors. They are specific little components whose only job is to provide a certain amount of resistance. So we need to be clear about the different language there between resistance and resistor. There are no resistors in this light bulb. There are wires that have resistance. Now, it gives us a clue here. The filament wires in the lamp are much thinner than the connecting wires. A thinner wire will be harder for current to get through. Imagine if we want to extend the analogy from the video I was talking about earlier with the students going to school, this is like trying to squeeze lots of students down a very narrow path. It's going to be harder for those students to get through. Fewer students will get along that path. each second. So the current would be lower because the resistance is higher in a thin wire. So think about the wire, think about the charges flowing through the wire. Think about what will happen if you make that wire narrower. Fewer charges can get through it. So first thing we're going to say here is that thinner wires have a higher resistance. Filament wires are thinner than the connecting wires, therefore have a higher resistance. High resistance, what happens if you have a high resistance is you're going to get more collisions between the electrons and the lattice of ions. Remember, the lattice of ions, it's just so the wire is made of copper. Copper is made of atoms. Okay, but when you pass electricity through it, the electrons leave the atoms, and you'll know from chemistry that when electrons leave an atom, it's no longer an atom; it's an ion because it's a charged atom, charged particle. So what electrical current is the flow of electrons through the wire. The lattice of ions is what's obstructing that. So if we have higher resistance, it means we have more likelihood that the electrons are going to collide with their ions, and if they do collide, that causes heat, that produces heat. So high resistance means more collisions between electrons and the ion lattice. This will cause the filament wire to heat up and therefore emit light. So this is how it's an old-fashioned light bulb. This is why they're so inefficient. Is the only way they produce light is by getting so hot that they glow red hot. The connecting wires have a low resistance, so there are fewer collisions. This means connecting wires are cooler and will not glow. And that's the end of P5. So on to P6 now, which P6, in my opinion, is often the more straightforward of the three sections. But when students attempted this paper, a number of mistakes prevented them scoring quite as highly as they could have done. So I'll be sure to highlight some of the more common mistakes I saw here. Question number 7. Ionizing radiation can damage and kill living cells. Part A, which of the following uses of radiation work by killing living cells? Put ticks in the boxes next to the 3 correct answers. The first thing, and I'm going to bang on about this again, 3 correct answers. And you see there's 2 marks available. That's not contradictory. Usually this kind of question, if you have, would for example, you would, if you put all 3 correct answers, you get 2 marks. If you put 2 correct answers, you get 1 mark. They may give you a mark for 1 correct answer. It would vary by question. So we need to have 3 ticks here. If you put, by the way, if you put 4 ticks in these boxes, straight away you're going to lose 1 mark from if they're correct, because every extra tick you put in will deduct 1 mark from any correct ticks that you have got. So detecting cracks in metal pipes, well, that is a use of radiation, but there are no living cells in the pipes or in the cracks, so that's not going to be correct. As a tracer in the body, now obviously the body does have living cells, but what a medical tracer is used for is when you either drink or you're injected with a radioactive chemical, and that radioactivity spreads around your body, and it passes out of your body, so that by using a special gamma camera, you can identify where in the body the highest concentrations of the radioactive sources, and it basically gives you an internal view of the body by using a gamma camera. So this is most certainly not about killing living cells. It's used sort of in a similar way to an X-ray or an MRI scan as a tracer. So it's not for killing living cells. Sterilizing surgical instruments. Well, things like scalpels used in surgery, you don't want any bacteria on them. You want to kill dead anything on those so that it doesn't infect the patient. So sterilizing surgical instruments definitely is about killing living cells, albeit very tiny single-celled organisms mostly. Irradiating food. This one's very similar. The food that is passed through manufacturing plants is sometimes bathed in gamma radiation. The reason for that is to kill any living cells on it. A common misconception with radioactivity is that by shining radioactivity, by shining radiation, gamma, alpha or beta, on something, it will make that thing radioactive. That's not the case. Remember, gamma radiation, it is light. It's high intensity, high frequency, high energy light, and it's no more true that shining radioactivity on something makes it radioactive than shining light on something makes it glow, makes it produce light. Okay, so by shining gamma radiation on food, you're not going to damage the food. The food is already dead, so you're not going to cause any cell mutations, but anything that is living on the food, for example, bacteria, will be killed. So this is a correct answer. Treating cancer, well, cancer cells are living. They are mutated cells. They may have been caused by radioactivity, but equally, that radioactivity can be used to kill the cells, the cancerous cells. So they target gamma radiation at them and kill these living cancer cells. So that one is correct. And then we've got our 3 correct answers, but let's just look at detecting smoke. Well, smoke is not living. Smoke is not a living bacteria. On to part B. People working with radioactive sources often wear detectors to often wear detectors to measure how much ionizing radiation they are exposed to. One type of detector is a badge with photographic film covered by 3 different materials. This is the sort of thing that would be worn by somebody working in a nuclear power plant, for example. The photographic film records the amount of radiation that reaches it, and the badge has 3 sections. Section A covered in lead, B covered in aluminium, and C covered with card. Behind those materials, there's a photographic film which will be exposed to the thing. So the idea here, I'm not going to scroll down just so we can keep this image up. The question asks you which sections can be used to detect beta and gamma radiation. Well, we need to consider which sections beta and gamma can get through. So beta radiation, you should know, can get through card, but it is stopped by aluminium and is definitely stopped by lead. So the beta will only be able to get through the card. It would be stopped by the aluminium. It wouldn't get through. So for beta, only C can be used. For the gamma radiation, gamma can certainly pass through card, and it can pass through aluminium, but you should have seen in class that when we put lead in front of gamma, it stops. You need quite a few centimeters of lead to stop it, but it does stop it. So gamma will work on B and C. That will get you both marks. A really common mistake in this question was to, instead of thinking about which ones it would get through, students thought about which ones it'd be stopped by. So they remembered that, oh, beta's stopped by aluminium, so beta would work on B, and they said, oh, well, gamma's stopped by lead, so gamma will start on A. You, in this particular example, you need the type of radiation has to be able to pass through the material for it to be any use. So only beta can only get through C, gamma can only get through B and C. So that was part I there. I've just explained it up here. The badge cannot be used to detect alpha radiation. Again, explain why. Well, let's have a look at alpha radiation. Alpha is definitely stopped by lead. It's definitely stopped by aluminium. And it also is stopped by card. You will have seen in class at some point a demonstration showing that alpha radiation is stopped by a single sheet of paper. So none of those three windows, none of those three coverings allow alpha radiation through. So that's what we need to write here. All of the windows, that is card, aluminium, and lead, block alpha radiation. So none of it reaches the film. We're very nearly there. On to question number 8. The energy from a nuclear reactor is produced using the nuclear fuel uranium. The reactor produces an average of 3 times 10 to the power of 9 joules of thermal energy per second. By the way, this question is exactly why I always remind students to take scientific calculators into physics exams, actually into all science exams, because you need the standard form function to be able to do any of these E equals mc squared calculations. Part AI, what mass of uranium will be uranium will be converted to energy by the power station during 1 second? The speed of light is 3 multiplied by 10 to the power of 8 meters per second. So the equation here, the most famous equation in physics, E equals mc squared, is the equation that relates a change in mass of a material during nuclear fission or nuclear fusion. It relates the change in mass of the material to the energy that's released as a result. We can rearrange that equation here because we're interested in mass. It's talking about per second. We can just go, right, in one snapshot of 1 second, it produces 3 times 10 to the 9 joules of energy. And in 1 second, we're interested in how much mass will be produced. So don't worry about the second here. So our mass equals, rearranging the equation, dividing both sides by c squared, mass equals E divided by c squared. So our E here is 3.0 times 10 to the power of 9 joules. And we're going to divide that by c squared. You've got to be really careful with brackets here. 3.0 times 10 to the power of 8, and we square all of that. So it becomes 9 times 10 to the power of 16. And our answer to that then comes out as 3.3 times 10 to the minus 3 kilograms. Just worth reflecting on that. That's 3 grams to produce that huge amount of energy. It was 3 grams of uranium. Because that links nicely into part 2 of this question. How does this compare with the mass of coal used in a coal-fired power station that produces the same amount of energy per second? Well, nuclear power is so attractive because it uses such tiny amounts of fuel, and the reason for that is that nuclear fission can release far more energy from the same amount of mass than a chemical reaction can. When you're burning something in a you're burning coal in a coal-fired power station, you're releasing the energy through combustion. That's a chemical reaction. So it will be a much greater mass of coal required because nuclear reactions release much more energy than chemical reactions. E part I, energy in the power station is produced by the fission of uranium. Complete this nuclear equation for a fission reaction in the power station. You should look forward to questions like this in an exam because these decay equations should be simple. I will highlight, though, the most common mistake that was made by students in the mock exams for this one. These decay equations represent the various particles that are participating in the fission reaction. You see here we have one neutron joins with a uranium-235 atom. Fission happens, which produces this zirconium, I think, atom 98, zirconium 98, a tellurium atom, or it could be, yeah, I think it's tellurium, it could be technetium. I'm no chemist, and this here, 3 neutrons. Now, the most common mistake was that students missed this big 3. It's just like in a chemical equation. If you have a big number before the particle, that means you've got 3 of them. So we have 3 neutrons here. On either side of our arrow, the mass number and the proton number need to add up. So, for example, here on this side of the arrow, we have 1 plus 235. So we have 236 as our combined mass number. And on the other side, we have 98 plus 3, so that's 101. So we need a number here that will make up to 236. So by adding 135, it now adds up. So 1 plus 235 is 236. 98 plus 135 plus 3, because there are 3 lots of this neutron, will give us 236. So the mass number adds up. And on the bottom, the proton number, 0 plus 92 is obviously 92. So we need to get 92 here as well. Well, we've got 3 times 0. Neutrons don't have any charge, so their proton number is 0. So we've only got 40 on this side at the moment, so we need to make that 40 up to 92. So we're going to do that by adding 52. So that gives us our atom here, which is 13552. I'm just reading some of the comments here. Did I say that the speed of light was 3 times 10 to the speed of light is 3 times 10 to the power of 8, which is what I did here. By squaring the speed of light, you end up with 9 times 10 to the power of 16. So you're doing 3 times 10 to the power of 9, which is the energy, divided by the speed of light squared. Sorry, my apologies. It is 3.3 times 10 to the minus 8. I have misread my own handwriting when I was copying this down. So yeah, the calculation here is incorrect for question 8. 3.3 times 10 to the minus 8, this should read. Which just goes to show you need to be very careful when you're copying down answers. Right. Part 2. Explain how the nuclear fission reaction is controlled in a nuclear power station. Include the following in your answer: chain reaction, fuel rod, control rod, coolant. So we need to explain the fission reaction. We need to use those keywords as part of it. So in other words, we need to be explaining what each of those things is. So a chain reaction is what produces the energy. We could, if you want to, here you can go into some detail about how a chain reaction happens. So one neutron causes nuclear fission, which releases 3 neutrons to cause fission in 3 more nuclei. Okay, so the reaction gets bigger and bigger and bigger each time. That's the chain reaction. You probably don't need that much detail. Fuel rods contain uranium, where the fission reactions take place. The purpose of the control rods is to absorb those excess neutrons. If you didn't have the control rods, the chain reaction would go crazy. You've got you're emitting 3 neutrons from each fission reaction. If that spreads and spreads and spreads, the reaction will get quickly out of control. And what you have is, instead of a nuclear power station, is a nuclear bomb. That's what a nuclear bomb is, with an out of control chain reaction. So the control rods absorb some of the neutrons to slow down chain reaction. And finally, the coolant absorbs the heat that is produced in the reaction. It's important here you don't just say the coolant cools it down. That's obvious. The job of the coolant is to absorb the heat that can then be used to generate electricity in the next stage of the power station. And the very last question is question number 9 here, is about the government's considering building more nuclear reactors. This question, by the way, is the easier of the 6-mark questions in this paper. That you normally would get 2 questions aimed at A students, and 1 question aimed at sort of C grade or B grade students. And this is the slightly easier one. It's mostly a recall of knowledge. So it's saying one of the arguments against using nuclear reactors to produce energy is that they produce radioactive waste. Are people in government right to worry about the risks of the different types of radioactive waste? And how they are disposed of? Explain your answer. Right. It's clear here that you need to talk about the risks. You need to talk about the different types of radioactive waste and how they're disposed of, and you need to explain your answer. So the first thing we need to talk about then is the risks. What are the risks related to radioactivity? So radioactive waste emits ionizing radiation. This can cause cancer. That's the risk. We need to consider now the different types of waste, and you simply need to learn these three types of waste, what they are and how they're disposed of. So the first one we'll deal with is high level waste. This is usually spent fuel rods. So nuclear fuel rods that have been used up, they are highly radioactive, very, very, very dangerous. They're normally, once they've cooled down, they're normally encased in glass and put at the bottom of the sea. The next one is medium level waste. This is usually equipment that's been handling the fuel rods. The risk is a medium risk. Usually this waste is stored underground. It's worth actually, let's add to our initial thoughts here about it causing cancer. We should also say it can take a very long time, thousands of years, to become safe. Is one of the problems with nuclear power. And the last one, low level waste. Sorry, let's just go back here. We'd normally refer to it not as medium level waste, but as intermediate level waste. Let's correct that. Low level waste, it's medical waste. So equipment that's been in contact with perhaps medical traces or anything like that. Low risk, usually just put in landfill. Okay, and so there you have. We have discussed. You've explained what the risks are of the different types of radioactive waste, and you've referred to the different types of radioactive waste as well, which brings us to the end of question 9. And that's the end of this exam paper. So what I'll do, I think, for maybe 15 minutes or so, or as long as the questions keep coming, I'll answer any questions. So if you want to make some comments in the comments box, bear in mind you're hearing me on a slight delay. So any questions? Robert asks what's predicted to come up. I have no idea. OCR are not predictable, unfortunately. Have a look in terms of 6 markers. Have a look back at what has come up in 6 mark questions before. It's usually, you can look through the spec, and some topics just simply won't be suitable for 6 marks from the specs, just because there's not enough to them. You know, fairly straightforward questions. For example, you won't get a 6 mark question, I would think, that said explain what a commutator does, because that's to do with electrical motors in P5, because you wouldn't be able to write enough stuff to do 6 marks. Having said that, you could get a question that would say explain how a motor works and why it requires a commutator. So a 6 mark question will usually require you to pull a significant chunk of knowledge out of your brain, or, as quite often happens, apply skills to an example that's been given to you. Yeah, for those of you in school tomorrow, I will be period 2, and I'll try and be available during the morning on Friday as well, at least for some of the time. What equations do you need to know that are not at the front of the paper? So we discussed speed is distance over time earlier. I think there was another equation that came up as well. Oh, the combination of resistors. So in series, you add up the resistors, and in parallel, you divide them by the number that you've got. So let me do an example. So if we have 3 resistors here, and each one is, let's say, 10 ohms, then the total resistance R total is going to be equal to 10 divided by 3. There is a more complex formula, so 3.3. There is a more complex formula that is used at A level, and you may come across that in some textbooks and some revision guides. At GCSE, you'll only be faced with resistors that are the same value, so this equation here will work. So basically, you take the value of the resistor and you divide it by the number of resistors you've got. For a series combination, you just add up the resistors in series, or if they're all the same as they are in this case, 10, 10, 10, then your R total is going to be equal to 3 times 10, which is 30. Sorry, there won't be another video tomorrow. The reason this is on today and not tomorrow is because I'm unavailable tomorrow evening. Vaishali asks, what if the resistors are different in resistance? They wouldn't give you a parallel combination with different resistors. If you want to look that up, feel free. There is an equation used at AS level, but for the purposes of this GCSE exam, you won't need to use that. Yes, I'm going to do a video on P7 next week, next Wednesday. Samir asks, what's induced energy? I think, are you talking about transformers and generators there, induced voltage? So when you move a wire in a magnetic field, you induce a voltage in that wire. Or in the case of a transformer, the voltage is induced because the magnetic field is moving around the wire. Okay, any more questions? Star asks, do we need to know the left-hand rule? You don't need to directly know the left-hand rule. It doesn't actually come up in OCR. But what you do need to know is that the voltage, sorry, the magnetic field, the current, and the force are at right angles to each other. And to be honest, the easiest way of remembering that is to remember the left-hand rule. So you have your field. So that's the first finger is the field, the magnetic field. The second finger is the current. And the thumb is the thrust of the motion. Samia says, do we need to know the two types of interactions? Can you just clarify that? I'm not sure what you mean by that. For P5, do we need to know voltage current graphs? I don't think so. I have to check the spec for that one. Just give me a second. By the way, the full spec for all of the physics units is available on cowenphysics.com. It's the same as what you'll get on the OCR website. But if you go to the GCSE and then to 21st Century Science P5 electric circuits, and you'll get the whole specification. There are the ones that are blue and are links will take you to a video about that topic. There aren't many, unfortunately, at the moment for the GCSE units. Okay, actually, if looking at the spec, there is describing words or using a sketch graph how the current through a component varies with voltage across it when the resistance stays constant. So it's looking for a simple directly proportional graph there as part of to represent Ohm's law. Okay, yes, Samia. So contact, interaction, action at a distance. That's something that comes within the textbook, and I don't really come across in the exams or in the spec very much. You should be aware that some forces act through a contact and some act at a distance, but it's not something I've seen come up in an exam specifically. Any more questions? Okay, if there are no more questions, the video will automatically be uploaded as soon as this is finished. So if you want to check back, run through any of it at your own pace, feel free. And I will be in school tomorrow to help with any other questions you have, and also on Friday. Good luck with your revision. Thank you very much. Samia, no, you don't need to know about the man Michael Faraday.